which is by Johannes Kellendonk, who will tell us about which algebraic components of the Ellis semigroup of a non-tame dynamical system are especially big.
Okay, thank you very much for the invitation. I hope you like semigroups, you like Ellis semigroups. I got drawn into them more from a mathematical physics point of view, so I'm not such an expert in dynamical system theory, but I hope with such a talk to get feedback, especially about things which I don't know and forgot and maybe are a bit wrong. So please don't be shy and tell me at the end it was all known or wrong or something. So I'm talking about the Ellis semigroup, and already Reem introduced us. So for me, in this talk, this will always be a minimal dynamical system, and T will be mostly abelian, at least as when it comes to my results. So now, as you know, this Ellis semigroup is a compactification of my group T, viewed as a subgroup of the homeomorphisms of a compact, and in my talk, metrizable space. So T is a subgroup of the homeomorphisms of X. It is going to be compact and metrizable. And now this is going to be the closure in the topology of pointwise convergence. So I'm looking at all functions from X to X with pointwise topology. I take its closure. That's the Ellis semigroup. Now, composition, as you know, is the product structure. And there is some difficulty in the fact that though this object is compact, it's not going to be topological in the sense that it's continuous in both arguments. It's only right topological, means that only right translation is only continuous. Now, Ellis introduced this object some time ago in the 60s, and the idea, roughly speaking, was that by studying properties of this Ellis semigroup, I would have properties, I could describe properties of my dynamical system. And there are, in my mind, sort of typically three types of properties which are interesting. For the first, you would say these are the topological properties of the semigroup viewed as right topological, a compact right topological semigroup. And then you could look at the topological properties of its maps of the elements of E. And then something which I find is a little bit neglected about what are the algebraic properties of E. What does this tell us about the dynamical system? Of course, there are lots of things are known here, but I find surprisingly few things are known in this subject here when it goes beyond groups. When E is a group, well, my theorem is related to distality. Or when is it a group of homeomorphisms? Well, it is related to equicontinuity. But what happens if I'm outside of the group regime? And I'm a little bit interested in that. So for me, I always like to convince people that the Ellis semigroup is important by just saying it does two things. So the first thing, what it does, I think, is that let's suppose that XT is minimal, that it maps a topological closure of an orbit to an algebraic orbit. So on the dynamical system side, I have a closure of a T orbit. And on the semigroup side, this corresponds simply to an orbit. So it exchanges a bit of topology against algebra. Right? For me, if I don't take closures, it's just algebra. So it algebraizes topology. That's my view. And the second is what Reem already explained, that it captures proximality. And of course, I repeat myself, but let me do it anyway. So we say that x and y in X are proximal if and only if the distance, the infimum of the distance, I choose a metric which is compatible with the topology e to the t x e to the t y. This is 0. Is that correct? I hope. And then this is equivalent, and that's why the Ellis semigroup is so nice, to saying that there's an element which identifies the points. So these two properties, I think, are everybody who is interested in dynamics should study this Ellis semigroup. And of course, it has been studied a lot. Now, today I'm going to focus on one property, which actually is the same than Reem was looking about. So I'll focus on tame. And since this is an independent talk, I repeat the definition. There are actually 3 ways to introduce it. Yeah.
Sorry, I'm confused with the one. So do you say that the system is minimal?
I require the system to be minimal, yeah.
Then closure of the orbit is the entire space.
Yeah. And the entire space is one E orbit.
But then 2 is saying that the space has to be proximal.
No.
The action. Ah, no, okay, sorry.
So I would like to focus on tameness, right? So I repeat the definition, and I repeat sort of, because about 3 ways to define it. First way was to say that any element of E is a bare class 1 function. And so it means that I only need to look at sequences and the limit points in order to get the elements of E. And this is equivalent to saying that the cardinality of E is relatively small. It's small or equal to the continuum. And then the third condition, I don't repeat because already Reem stated it, is namely that there is an independence. So T contains an independence sequence. So this was Karen Lee who introduced this and showed the equivalence, and this is the dichotomy of Rogan and Calagrand, which gives us this and all this. So this is the definition. Tame means one of these properties.
Three again, what is the assumption on T?
T?
Yeah, what is it? A Z? Is it a billion or what is it?
Yeah, here probably you need it. It should contain that. Yeah.
It contains.
It should contain that.
Well, that's the definition of non-tame, right? The independent sequence.
Yeah, yeah.
Just put a knot.
Yeah.
Okay. Sorry. So Now, if you look at this, this is sort of the simplest way to say it. Just say, well, it's small, it's big, right? And so my talk is about the question, if this is big, what parts of it are big? Why I'm asking this question? Because, well, let's look at the algebraic structure of the semigroup. The semigroup has lots of ideals, lots of idempotents, even contains groups. Let's focus on these parts, which are very natural. And then we can sort of be more precise about non-tame systems by not just saying, well, it's non-tame because the cardinality of E is contains the Stone-Check complexification of N or something, but by saying certain parts of it are actually big. Okay, so that's the topic of this talk. So let me tell you a little bit more about the algebraic properties of semigroup. So E, of course, X, E is contained in all functions from X to X, right? Now I'm looking at a function, and I'm looking at it in a strange way at this function. I say it has an image. Okay. And it has a partition. So what is this partition? Well, it's the partition induced by F. So it's given by all three images of points in the image. So my space is partitioned by F, right? It's an equivalence relation if you want. And then there's a map, tilde. And what does this map do? Actually, it maps a member of the partition to this element. So I have sort of a complicated way of writing a function. Instead of writing a function by F, I'm writing it by three things: an image, a partition, and this now turns out to be a bijection. Right? By construction, it's injective and surjective. So it's a bijection. So now I'm looking at two such things. So I have two functions, and I want to describe actually what is their composition in this sort of complicated way. Well, if I describe their composition, what would I have to do here? Well, I would take, right, the canonical projection associated to this partition and restrict it to this image. Right, so I have a canonical projection defined by this equivalence relation. Let me provide it. That's actually given by the members of my partition. So that's a canonical projection. If you write it like this. Can you process this? No?
Sorry, what is this X quotient out by tilde G?
So this is the quotient space whose equivalence classes are just given by PG. Right. And then I associate a point in X. It's member in this partition. Right. That's it. So I fill in here canonical projection of PG. And then, of course, the whole thing here describes somehow, I wanted to describe this guy. Okay. Now, of course, if you think about this, you would say, no, it doesn't work. Because it can only work if this image coincides with this image, and if this partition coincides with this partition. So that's a condition. Okay. So I put this condition. So suppose we have an idempotent. Right, such that the write it down here. Yeah, so that if I take the image of F and I look at the restriction of the idempotent to the image of F, so I restrict it, I land in the image of E, such that this is a bijection. And also, I look at the map which goes from the image of my idempotent into the partition of F. So this would be the canonical projection onto that equivalence relation. So that partition is a bijection. Then this thing works. Okay. And so you find that E in E is the minimal bilateral ideal of E. So it contains all F in E, which satisfy these properties.
So can E be any idempotent?
No, E should be minimal.
Yes. But we have a minimal.
Yeah, so we want E to be minimal. And what means minimal among idempotents of a semigroup, right? Minimal means that if E is another idempotent, then I say that E is more equal than P, if and only if EP equal to P.
So you want this for every F?
No, I want
So
pick a minimal idempotent in E.
yes, but the next line. So such that im F goes to im E is a bijection. So there's no quantifier on F.
Yeah. So let's write it properly.
This would be lost on it because if F is the identity,
Let's put such a way. That E is the minimal idempotent in your X. And now define these two properties. So star one, star two.
True for any F?
So that's for F in it. I'm looking for the F in E, which satisfy these two properties. And they form a minimal bilateral ideal, which is actually also this one. Okay, so I complete now this diagram here using these maps. So here, I'm looking only now at F and G, which are in this minimal bilateral ideal. Okay, so
Sorry, I'm very confused. So your condition, it implies there is only one minimal identity.
no,
So if you apply two different ones, then they got to be equal by what you wrote.
no,
No, because the star condition, star and star
No,
depend
but
on
the,
E.
the definition, if P is another idempotent, so suppose now that P is
Okay.
also minimal. It's only on one side, and it cannot be on both sides.
oh, this is just the condition to single out what means minimal.
Yeah, but the condition on the right,
Yeah,
it only has to be on one side, because if you have two minimal idempotents, like U and V, you have that UV is equal to U and VU is equal to V. I mean,
There's left minimal and there's right minimal.
I got this wrong.
but look, I mean, take P to be another minimal idempotent, and then E times P is equal to it's either E or P, yeah, it cannot be both.
I think you both if they're equal.
No. I think it's okay, just only on one side. I mean, it's only one of them. I don't know which one because I never.
You mean it's only on one side of them? No, there's something wrong.
Well, there's left minimal and there's right minimal.
No.
So,
How do you define minimal in a semigroup? It's
so is it, what kind of a,
let me try to remember myself.
Okay, Google, minimal idempotent.
Can you look in our paper, it's in project, right at the beginning.
they have paper for what?
Well, by trying to substitute it. So we'll look it up. I'm completing the diagram. Right, so by these two properties, I have these maps. Well, actually, I turned these around because these are not like this. So I go to this way. And here I go in this way. These are bijections, right? So it means that by commutation of this diagram, right, I have this map, and then also have this map here. This map is important, so I give it a name. I write it A, e.g. image G. And so you see that this minimal bilateral ideal, it has the following form. Well, there's a set I, which collects all possible images. There is going to be a group G and a set lambda, which collects all possible partitions coming from maps in this kernel, in this minimal bilateral ideal. Right. Now, G is a subgroup of the permutation group of the image E. It's a subgroup. So that's for a moment just a set, and that's also a set. And this here, A, now I write it as lambda I, is a matrix with an index set lambda cross I, which takes values in G. Well, and then theorem is that G is actually G is a group. A priori, you could think G is just a semigroup, but G is actually a group. And G is a group, and it's an important group. We call it the structure group. So what I want to tell you is that once you have a semigroup, under certain conditions, it will have a minimal bilateral ideal. This minimal bilateral ideal has a particular structure. The structure theory for these groups, for these minimal bilateral ideals had been developed 100 years ago by Rees and Suskovic. It has this type. And so naturally, I have parts of my Ellis semigroup which are important and which I can now sort of ask for, are they especially big if E is especially big? So if I have a system which is not tame, so I know that this is very big, is perhaps this very big, or this very big, or this very big.
Sorry, do you know that the ideal is very big? You only know that E is very big.
Yeah, but
so do you imply that the ideal is big?
that's part of the question.
Ah, okay.
Yeah, that's part of the question. Is this already big? So I come up with a couple of results which are known in that context, which I'm going to write down. All right. So there's something very important for later, namely, this is a subgroup, and the subgroup itself contains a subgroup, which is the subgroup which is generated by these matrix elements. Right. So I'm going to say gamma going to be the subgroup generated by the matrix elements. Play a role. Yeah, so that's going to be called the little structure group. And I don't know whether there are semigroup theorists. It's actually easy to see when you have this particular form here, what are the idempotents, right? Because if you do the multiplication, which I actually didn't write down, so what is the multiplication that this isomorphism? It's I. So here I have an element G in G, lambda times J H mu. Well, the multiplication will be, this one will win at the left, and here I will multiply, but it's a twisted multiplication by the matrix element A lambda J. So this is lambda, this is J. And then I have H, and then I have mu. So the matrix element twists the multiplication in the middle, and otherwise it looks like sort of a direct product. And with this form, it's easy to see what are the idempotents, because the idempotents are of the form where this G here is just the inverse of A lambda J. The idempotents in this form. And so you see that I cross lambda labels the idempotents. You also see what are the left ideals. The left ideals are those where I keep the right one fixed. Because mu determines this mu. So this mu determines the left ideal. And this I determines the right ideal. So the whole algebraic structure is nicely encoded in this form. The first result now would be the following. So let's suppose that xt is abelian minimal. Then R equivalent, the first thing would be there's only one point in this set lambda, which actually means that A has a unit minimal left ideal. And this is equivalent to proximality, so the proximal relation being transitive. That's actually a very old result, which was discovered right at the beginning of the theory. I don't know who did this, probably already Ellis. And the third point, which is sort of not obvious in the language of dynamical systems, but here now becomes rather quickly obvious, namely that this gamma is brilliant. A little structure group is brilliant. So that's the first result. It's not very difficult. But you see, it sort of makes a contact between proximality transitive, and as you know, proximality transitive for systems which have small enough fibers actually means almost automorphic. And so we are in the realm of things which Ring was discussing. So second result. Well, just recall results which are also very old, just to see how the thing goes. So if xt is minimal, well, and this though, then this is the same as saying that the semigroup actually is a group. And if it's a group, it of course has a unique minimal bilateral ideal, which is this group. And this group is then this group G. So if the semigroup is the group, then the structure group is the group.
So the statement is that if xt is minimal, then dicto is equivalent to thing on the right. Is this correct?
If x is minimal, then this stability
Yes, okay.
is this here. So the third result, which I would like to say that you can say a little bit more if this now is equicontinuous. But if the system is equicontinuous, because then you know that this is not just a group, it's a group of homeomorphisms, and actually it's simply the space itself. So sorry, here I know I'm supposing for this writing down that it's not only minimal but also abelian. Then E is G. X. So as you know, if you have an abelian group action equicontinuous, then I can define a group product on this space. And this group is going to be okay, and then well, the last thing, which is sort of, I put also down. So xt is almost automorphic. As you know, this means that the system is minimal and there is at least one point on which the factor map is injective. And then we have that this idea here is isomorphic to I cos G, and G is actually the maximal equicontinuous factor. So let me rewrite this a little bit nicer. It's an important point. I mean, Rehm was talking about the result by Wang and generalized by Glasner that tame systems for groups which have an invariant measure have to be almost automorphic. And so this means, so X be almost automorphic. So I have a factor onto its maximal equicontinuous factor, maximal equicontinuous factor. And so almost automorphic means that there exists a point that's at the fiber on this point of the image as cardinality 1. Okay. These were some of the easier results. Results. One result, which I also would like to put into context, also it doesn't directly say something about the final result, is a result which goes back to, I forgot the name, McMahon and Glasner. I'm not sure that I spelled this right. Maybe that's a Y. Glasner. Which also in the context of metrizable minimal reactions say the following. If the cardinality, they don't say it in these words, but it's about this. If the cardinality of this set lambda is small, like most then of the continuum, then this must be a PI flow. Right. So what is a PI flow? How much time do I have actually?
You have 7 minutes.
7 minutes. So I'm not going to write down exactly what is a PI flow, but a PI flow, so P stands for proximal, I for isometric. I can look at extensions which are either isometric or are proximal. We heard about proximal extensions a little bit by Tudor. And now I can look at towers. Right? So a PI flow, a strict PI flow, is the tower of extension, possibly transfinite, where all these extensions are either isometric or proximal. And a non-strict PI flow is a system which has a proximal extension, which is itself an AI, a tower of AI extensions. So it's a bit of a complicated notion. But anyway, this is something very much studied. And so you see that the cardinality of this guy tells me something about the nature of the dynamics. But I should say, like in the case of Riem, when we talk about tame systems, the converse need not be true. So, in other words, there are PI systems, PI flows, where the cardinality of this lambda here is larger than the cardinality of the continuum. So it's especially lambda. So now, these were all results which were known. Now I'm asking very specifically, can I say something when, can I give conditions which guarantee that it's G which is large, right? Why do I do that? Right, I just remember this condition here tells me that G for tame systems is small, but has to be anyway. But even the counterexamples, I mean, not the examples which Riem was producing in the Toeplitz shifts, there are many Toeplitz shifts which are not tame, but they are also all almost automorphic, so they all have a small G. So non-tameness does not imply that G has to be small. So I wonder, what do I need for G to be large? Okay, so that's the plan. So let me have a look at systems. Again, minimal, but now also Albanian. And I look at the maximal equicontinuous factor. Right. And I'm going to define the regular points of the maximal equicontinuous factor. Well, these are the points in the maximal equicontinuous factor, such that if I look at the fiber over this point, it contains only distal points. Non-proximal points. these are the regular points. I think this is sort of a standard definition. And of course, I have the singular points, which is going to be the complement. And everything sits in a group, so that's a group. And let me construct. So this is
X max in the
X max, it's X max. I wanted you to fill out this in your head actually here.
but also on the left.
Also, yeah, also there, you fill it out.
Why do you call it X max? Why do you call it Z max?
Or let me call it X.
Max is, okay.
Sorry, I called it X max. And now I'm going to look at the group, which is generated by the differences of this guy. Okay, so let me call that L. It's the group Z. And so fine. I'll let you fill out the max. So it's the group generated by this. So let me write down theorem, which is my theorem will tell me when G has to be huge. So let xt be minimal abelian, right? So if the quotient is uncountable, and proximality not transitive, then G is huge. Right, so meaning that the cardinality of G is at least that 2 to the.
You mean E is large,
Is
right?
sorry?
You mean E is large.
No, G. I'm interested in E is large anyway. I'm looking at something finer, and I want to see whether something finer is large. And I should say, well, this property that proximality is not that it's not transitive, right? This is sort of almost the opposite of being almost automorphic, right? So under some assumption, it's actually the opposite of being almost automorphic. So that I would like to add as a remark. So if there is at least one point, one regular point, such that the number of elements in this fiber is finite, then proximality being transitive is equivalent to almost for minimal abelian systems. So this condition sort of, if you are happy to be in this regime, is saying that if I'm not almost automorphic, then it is G under this condition, which is very huge. Okay, I suppose 7 minutes over. Do I have two minutes for the idea of the truth?
It says no.
Okay. The chef says no, I won't tell you.
So I think we should thank the speaker and somebody should ask about the idea of the truth. Yes, very nice. Any question first, which is not an idea of the truth?
Yes. So how easy is your condition to check? If I give you a system, can you tell me whether it is?
Well, there are, if I have only, if the singular points are only, if they're only countable.
Yes,
as singular points.
precisely, but what if they're uncountable? Can you?
I can't give you an example so far. No.
You don't.
Well, I mean, you see, my favorite examples are, of course, something like similar systems like constant length substitutions, right? Constant length substitutions, which are almost automorphic, so not total triplets. Then there is the class of those where only it's countably many. And there's the class who have uncountably many singular points. The uncountably many singular points are pretty difficult. And usually I cannot get this condition back.
You mean it's false or you cannot prove it?
It's false and sometimes.
Okay. So it just generates the whole group.
It generates everything, yeah.
So why do you take subtraction? Why do you take differences?
Why do you, well, that's the point about the proof. So this was a hint, right?
I had another question first.
Yeah.
Each time you say uncountable, you actually mean with the power of the continuum, right? You can never have anything between Aleph note and 2 to the Aleph notes, just because of the way these things are encoded.
You look, ask a logician.
That was a bit what's the law.
No, it's a real dichotomy. I mean, between continuum and 2 to the continuum.
No, between countable and continuum.
Well, there's nothing like that here. I mean, here the dichotomy is between continuum and 2 to.
Yeah, the dichotomy is.
And this is a real dichotomy because there could be cardinals between the two. I mean, so the real dichotomy is that either it is smaller than the continuum, so it injects in the counter space,
I understand.
or the ultra filters inject into. This is the real. I mean, this is how you prove this fact that the space beta n injects.
Yes, that's
So this is the way. So the real statement is there is actually an injection from beta n into this.
Right. But when we discuss on whether there are only countably many singular points or uncountably many,
yeah,
I'm pretty sure that they cannot be uncountably
Yes.
many.
So for
without there being a
I'm just
continuum.
thinking because this Ellis, it actually has to be countable for this to hold. Because otherwise, if this has the countable index,
it has to be countable.
Oh,
no, I'm just give me a second. No, sorry. Yeah, that was think what is that?
Other questions or remarks? Well, I'm not sure I understood some details of the proof. So can you elaborate a little bit on what Theodore just said? And can you give us some details on the proof?
So yeah, so
Just the idea.
that's the idea. So the first thing is that you show that proximality non-transitive. That's actually not very difficult. It's equivalent to the fact that the little structure group non-trivial. That's the first thing. Now the little structure group, what was it actually? It was, if I take the minimal idempotence and I look at the semigroup generated by those, then you show that this is going to be a subsemigroup of the minimal bilateral ideal of this form. So you only replace G by this little structure group. And then you realize that this guy acts on X non-trivially only on fibers which are singular. So if I take an element F in here, and here's my maximal equipotenuse factor, I take this fibers, there is a certain, let's say here, just kinematically, this is my singular set. Then this F will act trivially everywhere except on fibers which come from singular points. Why is that the case? Well, it's the case because in fibers here, all elements are non-proximal. And so idempotents on a non-proximal fiber have to act like the identity. So everything is identity here, something here. Now I do the trick, which you know. I use a section. It's cool for him now, which sort of moves me this set over here. I take a set in here. And if I have F here, then I have F minus 1. That's a new element in the Ellis semigroup, which acts non-trivially here and trivially everywhere else. Now, if I have enough of these sets to produce me independent subsets, then I can on each of these subsets produce functions which do something non-trivially only in the subset, but trivially outside. Then I take products. And in these products, I construct uncountably, 2 to the C different functions in the group. That's.
Where does the minus, what is the fraction coming from?
It comes from the fact that when I move this guy around, I don't have any overlap. Right, so I need to be sure that this one will not have overlap with this guy, because if this has overlap with this guy, then in the overlap, there's something which I cannot control.
Can I say one more thing? But I think, because I figured this out what I wanted to say. So I think instead of uncountable, you can put infinite, or you can just put L is not open. And all of these will be good.
Okay. L is not open.
Yeah.
Okay.
This will just be enough.
All right.
This is because some general nonsense thing. So this L is an analytic subgroup, and then if it is a countable index, it has to be open.
Okay.
I can explain this to them.
Yeah.
And you don't require that the fibers are bounded.
No.
No.
This is, I only need to be opposite to opposite.
Very good. Are there some questions or remarks from the online participants? No, just a nice thing, no.
Oh, thank you. I'll read it later, maybe.
No, thank you for your talk. It was an interesting talk, but I don't have further questions.
Okay, well, let's stop the recording.